Thank you for this introduction. My name is Hiroki Furue from the University of Tokyo, and this is joint work with Tsuyoshi Takagi. First, I'll talk about the background of this research. Multivariate public key crypto system constructed based on the difficulty of the MQ problem is known to be candidates for post-quantum crypto systems. And these schemes are mainly used for digital signature scheme, such as unbalanced oil and vinegar, called EOV. And MQ program can be written like this. Given a quadratic polynomial map F composed of m polynomials from F1 to Fm in the polynomial ring Fq x1 to xn, and then find one solution satisfying f a1 to an equals 0, like this. And the security of MPKC depends on, is not to depend on the difficulty of some algebraic problems, such as min-rank problem, other than the MQ problem. And this enumeration problem is also one of such problems. And let n and d be two positive integers and q be a prime power. Then given one single polynomial f in the polynomial q x1 to xn with degree d, then find outputs of f for all the inputs in fq. The algorithm solving this problem can be used as a foundational tool for some algebraic attacks, such as crow finding attack, hybrid approach, cross-bread, and polynomial Excel. And so, to estimate the complexity of solving this enumeration problem is very important to estimate the security of multivariate public key crypto systems. First, I talk about the classical approach solving this enumeration problem. For any inputs A1 to AN in FQ, this classical approach directly substitutes the input A1 to AN for F for any and iterate such a substitution Q to the N times. And then this polynomial F can be decomposed into two polynomials, F1 to F2, and F1 is n variables and degree d minus 1, and F2 is n minus 1 variables and degree d. And iterating such a decomposition, we can perform the substitution with the complexity order n plus d choose d. And so the time complexity of solving the enumeration problem for all the inputs is given as order n plus d choose d times q to the n. But there exists a more fast enumeration algorithm in the binary field case proposed by Boyle-Gate et al. At CHES 2010. They show that in the binary field, the enumeration problem can be solved by only order d times 2 to the n operations after negligible initialization phase. This algorithm is constructed by using Greykos and derivatives. And in this research, we propose a new algorithm solving this enumeration problem in the finite field with q element with a prime number pq. And we show that the enumeration problem can be solved by order d times q to the n operations after initialization phase. And this means that our proposed algorithm is equivalently efficient to the result of Boyle-Gate et al. And we can also apply our proposed algorithm into the case of FPR with prime number p and positive integer r. Then I'll talk about the result of Boyle-Gate et al. In the binary field. As I said before, the enumeration algorithm of the Boyer-Gate-Ito is constructed mainly by using two techniques, and one of them is this gray code. Gray code is an ordering of the binary vector space such that two successive values always differ in only one bit. For example, in the standard-based system, for example, 001 and 010 differ in 2 bits, the second and third bit, but in the gray code ordering, any successive pair differs in only 1 bit. And another technique is derivatives in the binary field. For any n-dimensional vector x1, x over the binary field and the unit vector ei, and the ith derivative of f, del I fx, is defined as fx plus ei plus fx. Then by using this definition in the enumeration algorithm of Boyer-Gate-Ito, they compute the value of fx plus ei by adding fx and del I fx. For example, it holds del I1 equals 0 and del I xi equals 1. And if the degree of f is d, then the degree of del I f is lower than or equal to d minus 1. Then I roughly explain the enumeration algorithm of Boyer-Gate-Ito in the case of the d equals 1. And this d is the degree of the given polynomial f. If degree f equals 1, then the derivative values del I f is constant, and we set del I f as ci. In the case of n equals 3, like this, we compute all the output in the order of gray code. And first, we evaluate f at the initial point, 0, 0, 0. And then f001 is only 0, 0, 0 and 0, 0, 1 differ in only the third bit. And thus, from the definition of derivatives, we can compute the value f001 by adding f00 and del 3f000 equals C3. By iterating such an addition of derivative values, we can enumerate all the outputs starting from f00 to f100. Next was the case of d is larger than 1. In this case, we also enumerate all the output by using derivative and gray code ordering. But unlike the case of d equals 1, these derivatives del if is not constant and degree d minus 1 polynomial with high probability. If we evaluate these derivatives directly by directly substituting the input, it will be not more efficient compared with the classical approach. So we want to also evaluate these derivative values by using gray code ordering and its derivatives. And when we focus on the third derivative, del 3f, and then we want to evaluate del 3f at these 4 points, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. And these 4 values is not seem to be in the gray code ordering. But in the finite field, but in the binary field, it holds xi squared equals xi, and thus del if does not include xi. So we can cancel the third variables here, and we can regard as this del 3f as the function with 2 variables x1 and x2, and these 0, 0, 0, 1, 1, 1, 1, 0 can be seen as gray code ordering. Like this, we can recursively enumerate all derivative values in the order of gray codes using derivatives. And so the time complexity is given as order d times 2 to the n plus negligible initial phase complexity order n to the 2d. And then it's natural to consider the extension of the enumeration algorithm of Boyer-Get et al. To the case of FQ with Q not equals 2. We here consider to apply the Boyer-Get et al.'s algorithm to the case of Q equals 3 and N equals 3. But unlike the case of Q equals 2, it doesn't hold xi squared equals xi in FQ. So these del 3f cannot be enumerated in the order of gray codes. And this is the reason why we cannot apply the Boyer-Get et al.'s enumeration algorithm into the case of FQ with Q with a prime number Q. Next about our proposed algorithm in the finite field FQ. We here suppose that FQ is a prime number Q, and we also use derivatives in FQ defined like this: del I fx equals fx plus ei minus fx. And we use our enumeration algorithm uses lexicographic ordering instead of gray codes used in the enumeration algorithm of Boyer-Get et al. And in the gray code ordering, the output is covered like this: f00, f01, f11, f10. But in our lexicographic order, like this, we first compute f00, and then by adding derivatives, we obtain f01 and f02. And then return to f00, and by adding derivatives, compute f10. Like this, by using branching structure, we realize lexicographic order enumeration. And this is a more formal description. For any n-dimensional vector over FQX with like this form, xk is a non-zero element, and the last n minus k elements are zeros. And n-dimensional vector A over non-negative integers representing the degree of derivatives. Then the derivative del AF defined like this: del n A1 to del n AN of the output of del AF for this X is computed in the proposed algorithm like this: del AF x1 to xk minus 1, xk minus 1, 0 to 0, plus del AF plus EKF. This means that the case derivative of del AF x1 to xk minus 1 to xk minus 1, 0 to 0. Then following this formula, we can enumerate the given polynomial f like this lexicographic order. And the important thing is for these 6 points of del 2f required to complete the enumeration of f, we can also enumerate these 6 points del 2f following the above formula in the lexicographic order. And so we can recursively enumerate all derivatives in lexicographic order. To realize such a branching structure in lexicographic order, we store some outputs for each derivative, del AF, unlike the enumeration algorithm of Boyer-Get et al. Actually, here DAK stores the output of the F with the input like this form. The kth element is non-zero, and the last n minus k elements are zeros. Then, like this, these F00, F10, F20 are stored in this D001, and other 6 elements are stored in D002. By using this data structure, we can realize enumeration in lexicographic order with branching structure. This structure brings us only small cost of memory consumption compared with enumeration algorithm of Boyer-Get et al. For example, for input f equals to x1 squared plus x1 plus x1 x2 plus x2 plus 1 in the finite field with 3 elements, f3. First, we compute the output of f00 and store it in D001. And then, by adding derivatives there to f00 into D00 into f00, we can compute f01 and store it in D002. And similarly, we compute f02 and store it in D002. And then return to f00 stored in D001. By adding del 1 f00 into f00, we can obtain f10 and store it in D001. Like this, by storing some outputs separately, we can realize such a branching structure in lexicographic order. We have finally discussed the complexity of our proposed algorithm. For each input, the update requires only order D manipulations, or like the Boyer-Get et al.'s enumeration algorithm. And so the time complexity of our proposed algorithm is given as order D times q to the n plus negligible initial, the complexity of negligible initial phase, order n plus d choose d squared. From this complexity, we can say that our proposed algorithm is equivalently efficient to the enumeration algorithm of Boyer-Get et al., like this. And we can also apply our proposed algorithm to the case of FPR with a prime P and integer R, a positive integer R. Given a polynomial f of n variables in FPR, then we can clearly transform it to R polynomials of R times n variables in the base field Fp. And so by applying our proposed algorithm on each F1 to Fr, we can enumerate all the outputs of the original polynomial f. Then the time complexity is given as order R times D times P to the R times n. Finally, we conclude this talk. In this talk, we construct a new enumeration algorithm for a single polynomial over finite fields with Fq with a prime number q. Our proposed algorithm achieves an equivalent efficiency to the enumeration algorithm of Boyer-Get et al. In the binary field. And the proposed algorithm is applicable to general finite fields Fp to the R with a small cost. And finally, it can be used to solve the MQ problem more efficiently compared with natural exhaustive search, like the result of the enumeration algorithm of Boyer-Get et al. That's all. Thank you for listening.
Yeah, we have already question lined up, so please.
Okay.
Have you looked into how this is applicable to the double matrix exponentiation routine algorithm which was presented 2 talks ago?
Sorry.
Maybe speak slower, please.
Okay. 2 talks ago, a speaker presented the DME signature algorithm, which used a large characteristic finite field multivariate. Is your algorithm applicable to that? And if so, what does it look like?
I'm sorry, I don't know much about the.
You understand the question, right? You understand this one?
Maybe I.
He's talking about DME.
Okay.
Yes.
I'm sorry, I don't know much about the information set decoding algorithm.
Okay.
But if the number of finite fields is odd characteristic, then it maybe can combined with other algorithm as a subroutine. So if it's possible, then it can affect the security of such a code-based.
Thank you.
Thank you.
Any other question? If not, I can ask a question. Can you go back to the slides before, please? It's here. No, just. Can you explain to us where this R coming from in the extension field? Where do you get this R? In the complexity.
Okay. Do you mean the complexity of it over FPR?
Yeah, FPR.
Okay. This is computed by naturally substituting these R times N and P and to the above complexity formula. Okay, sorry.
Any other question? If not, let's thank the speaker again, please.